Together with Mark Hoffman, I am one of co-leads of two projects, of a project JaCoCo, Java Code Coverage, and Eclipse ECLEMA, which integrates JaCoCo into Eclipse IDE. Unfortunately, Mark is not here, but I'm here. Here is my usual disclaimer. Whatever I'm going to say today, I'm going to say on my own. It's not connected with the company where I work. Nevertheless, it's a great company, SonarSource, if you know. Maybe you like, maybe you don't. And let's try to avoid cliché today. Let's, for once, start from the questions. Let's start from the questions from me. So I'm curious who came here to hear something about like code coverage, how to do it, how to measure it, whatever. Is there such people? Sorry for you, it's not going to be about that. Who came here to learn something about JaCoCo? Okay. The others, I guess you already know JaCoCo, right? You know the tool, you use it. Okay, great. Who came here to learn something new about Java? Good news for you. Hopefully, we will learn something new about Java. And primarily today, we're going to talk about the deep internal mechanics of how code coverage is computed on Java virtual machine. Not about the result, about the process, about implementation details. Dragons are here, be warned. So we're going to talk about this based on the experience of development for about 10 years of a library, JaCoCo, which was started as a replacement for very, very old library Emma, and later which replaced it in ECLEMA plugin, it replaced Emma, so that plugin now is fully based on JaCoCo. Later on, ECLEMA became an Eclipse project, etc., etc. The reason to replace Emma was that Emma stopped its evolution on Java 5, whereas there was Java 6, 7, and now it's 9, 10, 11, 12, and now it's even hard to count. So we have a wide range of experience with different JVM versions, and about this we're going to talk today. So we test, as of today, we test 9.5 major JDK versions. Why we test, we're going to see. One of the reasons that we find bugs out of this testing, and funny thing is that we find bugs not just in JaCoCo, sometimes in JaCoCo, but quite often we find bugs in actually JDK, in JVM. We're going to see which bugs, how do we find them, and funny fact, out of this, apparently we are one of the top contributors of bug reporters to the JDK. And here is a real disclaimer, actually. So the real disclaimer is, sorry, we're going to look again into internals of JVM. If you're not sure, maybe it's still time to leave the room. Sorry for that. We're going to talk a strong language. We're going to talk on few aspects about bytecode. Sorry for this. I will try to do intense violence of your brain. If you're not ready, please maybe leave from now. And again, warning, dragons here, all of these implementation details, it could change, etc., etc. There is some nasty tricks, hacks. Please, if unsure, don't use in production, etc., etc. So, if you are ready, let's start. Measurement, code coverage measurement. As soon as we talk about some measurement, I think it's important to remind such a term as observer effect, which comes from physics. You could see the quote from Wikipedia, but in short, it's simple as that. Any instrumentation is going to alter state of what is measured. That's it. No matter what you do, any process of measurement is going to alter state of a measured object. And when we talk about code coverage on JVM, it's a measurement. So we anyway alter the state of what we measure. So we alter the state of your program. And For us, for developers of such a tool, the important thing is to minimize that effect. We couldn't get rid of it. It's important to understand. But minimize we could. So keep that in mind. You will see that some of our decisions are based exactly on this, exactly on the fact that we should minimize effects. So when we speak about code coverage, there is different options to do it on the JVM. You could do runtime profiling, you could use debugger interfaces, etc., etc. It's not very efficient. It's quite slow. There are some prototypes of this, but it's not nice. Another interesting approach is instrumentation. Starting from Java 5, you could easily change classes of application by doing instrumentation. Forgot. Another approach to do instrumentation, basically instrumentation, it's a process of modification of the program to do some additional measurement. Of course, you could do such instrumentation based on the source code. So, for example, code coverage tool, which is Clover, which is originally was commercial product from Atlassian, now it's Open Clover, open source. It's a source-based instrumentation. So they take a source code, they modify it, then you need to compile it again, then you need to run it, and that's how you get the measurement. We find this is not so nice because you need to redo this cycle of rebuild. And you need to be careful to not actually leak such instrumented artifact into production. We find that it's much nicer to do the bytecode instrumentation, where on the fly we could modify the classes of your application to do the measurement. And once you stop at the application, your classes on the disk are exactly the same as they was before, because it was happening on the fly. For the reasons that on-the-fly instrumentation is not available in some scenarios like Android, we also provide offline, which means that even on the disk you could modify the classes. But we do recommend on-the-fly instrumentation. So at the end, it's as easy as just setting one more option for your JVM. You have your application, you usually start it like Java and application. With the code coverage agent, it's just additional option minus Java agent, da-da-da. So all like plugins for Gradle, Maven, and whatever, all of them, they boil down to just this single line under the hood. And of course, by application, you could have here your Tomcat, your WebLogic, whatever you want. One of the common scenarios is by application here, you have a unit test runner, GUnit. What happens at runtime? At runtime, agent implements a special pre-main method, which is executed by JVM before your main method. This pre-main method says, well, I would like to add such a transformer to transform all the classes ever loaded by the JVM. Bam. So we do work on class files. It's important also to understand. So you give us class files. JVM actually gives us class files. We do instrumentation, we change it somehow, we're going to see how. Then you execute already instrumented version. We collect the information out of this execution and instrumentation. And then we could do the analysis, taking original class files, runtime information. We do the analysis and generate the report. So what this instrumentation is, your program is some control flow graph. If we know that certain points of this control flow graph were reached, we could easily infer what before those points was also reached. So in this example, for example, if we know that the last red point was reached, so we came to the end of the method, for example, it means that the block just before, which is, let's say, one instruction, it was also executed. In certain places, we might have ifs, so we need to add some additional props. And in this example, if the prop on the left was executed, we know which of two branches was taken. If prop on the right was executed, we know that it's the other branch. If both those points were reached. We know that both branches were reached. And we don't need to insert actually anything before this branch, because, well, if we know that one of those branches was reached, then all the instructions before also were reached. So we choose a little amount of places where we need to insert probes, yet sufficient to compute and tell which instructions were executed. This is quite important. First of all, this is a way to minimize observer effect. So we try to add as little code as possible in order to not slow down your application. Second interesting thing here is, which is usually a user-faced problem, is that if one of those instructions on the way to some of the probes throws exception, we could not determine where we stopped. We can only say that we didn't reach the probe. So if, for example, you throw exception at the very start of your method, then you have, so basically, yeah, then you have something else. We wouldn't be able to say whether it was the very first instruction or the second one. That's a price that we need to pay, because unfortunately, every instruction in JVM could throw an exception. So if you would like to know about all happened exceptions, we would be inserting probes everywhere, and your performance of such instrumented application will be horrible. So how do we insert probes? Well, if you have some sequence of instructions and we just need to measure whether the instructions above was executed, we could just insert the probe in this sequence. If we have a method return, we should insert the probe just before return. This gives us a knowledge that we reached the end of the method. If we have some unconditional jumps, we could insert the probe just before this conditional jump and know that jump was executed. And as was shown before, we need to cover conditional jumps, which do have two branches. Here we could have a little trick for technical reasons. We need to invert the condition, and on inverted condition, it's way easier for us to insert probe. So we have those four strategies, and those four strategies is enough to modify your bytecode with sufficient amount of probes to compute code coverage. So I say it many, many times, probe, probe, probe. What this actually means, what the probe is. We have the requirement for probe. So again, this point in execution should have minimal runtime overhead. Yet, it shouldn't have side effects on your application's code. It should be thread safe, again, no side effects. And yet, it should record the fact of execution. It should record the fact that we reached this point. And it should be identifiable. So knowing that we reached this probe, we should be able to come back to your class file and say, well, we reached this point. Do you have any ideas of Java language construction which satisfies all those requirements? Thread safe, identifiable, records the fact that something was executed. It's actually pretty easy. The construction is super simple. It's a Boolean array equal true. The position is in the array gives us identification. We could just enumerate all the points which we want to insert probes by IDs from 0 to whatever we need. Boolean array, because we want to record whether it was executed or not, by default was not so false. Once it was executed, true. Thread safety. Well, no matter how many times you write true, it will be true at the end. Default false. This is nice construction. It's quite hard to come up with something smaller or better which yet satisfies those requirements. In the bytecode, this adds about from 4 to 7 bytes into the class file. So if you have 100 probes, well, we just need to add 400 bytes, let's say. So this is how instrumented code looks like. We just ask the JaCoCo runtime, please give me this array for my class. Then in certain points, we have those probes. We record the fact that something was executed, and that's it. This is a sketch of how instrumented class looks like. And here, we're going to see an interesting aspect of JVM, which is class loaders. Imagine that we have such a restrictive class loader. It does only one thing. It checks whether the name that we'd like to load starts with Java something, so basically Java lang, or starts with orgs_source something. And if it does not, it doesn't allow to load the class. Simple. Unfortunately, this imposes a problem. This construction going to some runtime into some package, it's actually not going to work. Because we couldn't, from instrumented class, which was loaded by such restrictive class loader, we can access only Java lang something, nothing else. How we could solve that? We tried different things, but what does not change is the fact that we need to have something inside of Java lang to guarantee that this can be accessed from any instrumented class. So at an agent startup, we go to the well-known Java class. In latest version, it's Java lang unknown year, and we add into this class a field. And through this field, our runtime could communicate with instrumented classes. We gave up on some other classes like Java lang void, Java util UUID, because unfortunately those classes, they were used at startup in different scenarios at startup of JVM. And once class is used, you could not modify its scheme, you couldn't add fields. So at the end, we ended up with Java lang unknown year, because it's so not so used class that we could use it. Then having this field, we could do another nice trick. We could call its method equals in order to pass whatever arguments we want to pass. And this construction allows us to use only APIs that exist in Java lang. In this code, there is nothing from org JaCoCo package. And there is no methods that are not known to JVM. So we could easily pass the boundaries of any class loader, or for SGI, whatever. And that's nice that actually in Java, you could do such a cast. You could get back a Boolean array. It's nice that in Java, arrays are actually mutable. So we give array as an argument, and we get back the result through the argument. Even this equals method returns not a Boolean array, but just a Boolean. So let's continue. In Java 9, we can do better. We can do way better, because in Java 9, there is Java lang invoke method handles lookup define class. This one allows us to actually go into the Java lang package and define new class here without modifying an existing one. To correct this solution a little bit more for Java 9, we also actually need to modify modulus, because you could not just go and modify Java lang, because Java lang is part of GDK, and it's defined as a module, and actually you couldn't do private lookup on this module. But fortunately, Java agents got another API, which is Java lang instrument redefine module. So at startup, we could easily say, okay, fine, we get a private access into Java lang. That's nice. Let's continue. As we talk about Java evolution, as we talk about usage of new Java 9 features, let's talk further. Java evolves. So Nowadays, bytecode versions increment differently than before. Basically now, every 6 months, bytecode version gets incremented, even if there is no changes in the bytecode. If there is no changes in semantic, it just routinely gets incremented each time new JDK is released. 12 increment, 13 increment. This imposes a little problem, because if you will take a new early access build of Java, like for example 9 when it wasn't released, if you will compile it and will try to read it using a bytecode manipulation library grade 1 such as ISM, you will get illegal argument exception, because this library simply could not read this version. It doesn't know it yet. This is a little bit of a chicken and an egg, because you couldn't release the library with the support of something which was not released. And how would you test the Java 9 early access build, whether you're compatible with it? It's unclear. Fun fact, if you use Java standard decompiler, JavaP, this beast actually doesn't check version, and this beast tries at best to decompile whatever it can. Unfortunately, sometimes it could fail when it will see the instructions that it doesn't understand, just because it doesn't check a version. So again, Dragons here, solution for this. Before passing the class bytes to the ISM bytecode manipulation library, we modify those class bytes pretending that it's one version lower. So basically pretending that it's the version that ISM could read. ISM successfully reads it, and we restore class bytes back. This works as long as increment really doesn't introduce new bytecode instructions. So it worked like for 14, there was no new bytecode introduction introduced. It worked for 9. It worked a little bit in between. This trick is not going to work probably for 14, because maybe there will be records which would change the bytecode. This trick is quite important for us, because it allows us to test a combination of our product with the JDK and provide the feedback in advance before the release. And also there is quite a big amount of people who actually test early access builds, and they would like to also compute the coverage. So this was a nice trick. Boom. I hope you warm it up enough. We have about half of a time. So, warm it, ready for hardcore? Let's have a look at Java assertions. So, this is Java assert statement on a simple Boolean. Anybody knows how this looks when compiled into the bytecode? Let's don't guess. We can decompile, we take JavaP decompiler, we decompile this example, and we are going to see crazy beast. In this crazy beast, we are going to see multiple conditions. We are going to see the read of a field, whereas in this class we do not have a field. Basically, to make your life a little bit simpler, we are going to see something like this. We are going to see that the class contains a new field which is not presented in the source code. And we are going to see that there is 2 checks of conditions. One check looks at the field, the other check looks at the actual conditions that we wrote. Why so happens? Why Java compiler implemented assertions like this? Exactly. JVM allows you to specify whether assertions enabled or disabled. It's not a compile time thing, it's a runtime thing. Furthermore, you can disable or enable assertions per class. For one class, you can enable, for others, disable. Which means that at runtime, for every loaded class, this class should first go to the runtime and ask the question, am I allowed to execute assertions or not? This is quite costly to go to some runtime and check this fact. So in order to avoid this cost, this status of assertions, whether they enabled or disabled, is cached in a field. Here's this field. This is actually a nice idea. We could do the same. Because in each instrumented method, we do not need to always load from the runtime a big array. We could just cache it into the special fields that we will add to all of your classes. Ready? If you have a such code, what's going to happen? Let's say assertions disabled. This compiles, yeah. No need to say that this doesn't compile. Assertions disabled. Okay, nothing. Assertions enabled. Assertion error. It's going to be assertion error in both cases. Exactly. So, remember how assertions implemented. It's synthetic Boolean field, which is initialized in a static initializer of a class. So the request to runtime happens at a static initializer. Default value for Booleans is false. The name of a field, assertions disabled, default false. At execution time, in order to create child, we first need to create its base. In order to create its base, we need to execute static initializer of the base. In order to execute static initializer of the base, we need to call the method some method. So we are going to execute some method far before the child class is actually initialized. So at the time when assertion is executed, assertions disabled field still has a default value false. And this assertion fails, no matter which flag to JVM you pass. There is an open bug on this. It's probably never going to be fixed. But you cannot disable assertions in this case. This is an interesting example. We call it bad cycle. It is a bad cycle when base class somehow manages to access a child. It introduces such initialization cycle. This is a little bit synthetic example because I wrote it knowing that it happens. And effect of this is quite observable. Assertion fails. In reality, people write a code like this without really realizing this. It just works somehow. There is some hidden games, but bam. This is a problem for us because we do exactly the same trick as assertions. And default value in the case of a Boolean array is null. So as long as we do not initialize this Boolean and there is such a bad cycle, user might get null pointer exception. And what was happening in reality is we were getting reports like, well, my code works without your library, my code is absolutely correct. As soon as I add your library, I get a null pointer exception. Please fix your library. Well, at the end, the problem is in the original code because there is such crazy initialization cycle, but we need to fix our library indeed, to not, again, introduce such effects on your application, to not change its behavior. You had initialization cycle, okay, you're going to have it anyway without null pointer exception. So the solution, we added one more method which does initialization. How it does initialization? Well, it just checks if we initialize it, then let's just return the value known. If we not yet initialize it, if we still have a null, then let's initialize. And now instead of reading from the field, we always go through the initialization method to guarantee that no matter whether static initialization block was executed or not, we anyway gonna get some non-null value. One might ask a question whether it is really a solution or not, because actually Java virtual machine specification says that you can use put static instruction to initialize, to put something into static final field. we have this static final field, and we write into it at some moment in time. So we do use put static bytecode instruction to write into this field, and Java virtual machine specification says, as soon as you have a final field and you use put static, then this put static must only occur in a so-called CLinit method, special method which is reserved for static initializers. So otherwise, illegal access error happens. So you could write into static final only from static initializers. We've been producing code like this for years. It was working. It was perfectly working. Why? Because this condition was not checked till some JDK version. They checked it in JDK 9 for whatever reasons, only for certain class versions. That's also why we need to test a wide range of different compilers and JVMs, because changes happen in JDK for certain class file versions. If we compile the same code and for Java 5, it's still going to work. Bam. So one might say, yeah, super simple, correct solution. Let's make field non-final. It's OK. Final doesn't bother, whether final or not, doesn't bother here. Unfortunately, we have a problem. Everything in interfaces is again static final, implicitly. In interfaces, it should be static final. One might say, why do you need to inject some fields into interfaces? Why do you need to measure code coverage on interfaces? Well, yes, because there is a default methods. What do we do? First, let's try to answer on the question whether bad cycles are possible with interfaces or not. Because if bad cycles are not possible with interfaces, then we do not need to use the same trick as before with addition of special method. In this case, we would just use static initialization method. Bad cycles are not possible with interfaces. Null pointer exception is not possible. Everything is OK. So first, let's try to construct bad cycle with interfaces. And in order to do so, we will read another Bible, which is Java language specification. In chapter about initialization, it says a lot. We need to remember only following words. Interface initialize it immediately before one of two. An instance of interface is created, or static method of this interface is invoked. Then, when class or interface initialized, then its superclasses are initialized as well as any super interfaces that declare default methods. That's important. So, bad cycle with interfaces. To trigger initialization, we need to either call static methods or create an instance. Here we are. We are going to have base interface. In order for initialization to happen, according to what we just read, we need to have a default method in it. Here it is. The very first line, it's exactly equivalent of what we've seen before. It's a call of a child during the static interface initialization. And here is a child. The method which we are calling in this child, default one, and another object constructed here for the reason that we would like to have a little bit of debug output. Once we execute this, if we see that line is printed before the exception is thrown, then all is OK, child is initialized before the base, method is not executed before the child is initialized. If we first gonna see the exception, then, well, child is not initialized, and the call of a method happened as before with bad cycles on classes. Call of a method happened before the initialization completed. We can vote because I guess you do not know what is going to happen. But we can vote. Who thinks that there is no bad cycle problem and class is going to be, interface is going to be initialized before the method is called? I think so. Who thinks opposite? Who are the other people? But you're right. Because the actual answer, well, it depends. Such a sequence is going to happen for GDK slower than 8 update 40. Such a sequence is going to happen with a crash of JVM because we throw an exception. If we create an instance, if we call a static method to trigger initialization, then such a sequence are going to happen without crash of JVM. On the versions from 8 update 40 up to 8 update 152. And everything what is upper, we're going to see another sequence. We stepped on all of this, and it was quite funny. Together with Mark, we've been in 2 different countries, trying exactly the same example that we just crafted with you, trying to execute it to understand what happens at runtime. He was getting one sequence, I was getting another sequence. And we wasn't believing our eyes because, well, how could it be? But then we checked which versions we are running and we realized that it's change of runtime behavior. So actually it was at the end, everything which is past update 152 GDK 8, it's actually a fixed correct behavior. And the fixed correct behavior says that actually in case of interfaces, child should be initialized before the base, and child method is never going to be called before child is initialized. So in fact, in case of interfaces, bad cycles are not possible. And after this all was uncovered, we participated in discovery of this. I think even Java language specification was a little bit adjusted to explicitly state that. Unfortunately, because there is a little bit of GDK's range which do have a problem, we anyway need to do some solution. And indeed, solution is like this. We couldn't declare field as non-final, so we couldn't actually initialize it. So in the method that each method is calling, we will be always checking for null, and we will be for a while having a slow pass for such GDKs where field is not initialized. Well, let's continue. So what we got at the end, this is how your instrumented class looks like. You have your instrumented method. Inside of this method, there is a local props array, which is requested from the runtime through additional method which we add. And we also have additional field for the performance reasons. There is a problem. Many people use reflection. Many people are going to ask from their own class, hey, dear friend, please tell me how many fields do you have? And many people surprised that their class, which doesn't declare any field, actually contains some field. We receive about 2 questions how that is possible each time when I'm using JaCoCo, how it's possible that I'm getting +1 field. We receive 2 such questions a month. Answer is, well, your reflection should be fixed. You should ignore synthetic fields. Even compiler, in case of certain situations, adds synthetic fields, like assertions, they add synthetic fields. Unfortunately, it's kind of not so nice to always answer the same question and always receive the same question. So we decided to go further. We would like to kill the field. And actually, Java evolves. That's great. That's cool. Java allows us to kill this field. In Java 11, there is dynamic class file constants. So call it condi. Condy allows to replace the field by a special low dynamic constant condy instruction, which is gonna call so-called bootstrap method, which returns the value that JVM will remember and will be returning each time the condy is executed. So this is a natural way to implement what we've been just implementing before, to initialize some field without exposing this field to the reflection. Unfortunately, what happens, the condy is available as a great feature in Java 11, but there is no single use of condy in JDK itself. It doesn't use it when compiles your code. It doesn't use it for its own purposes. The feature is there, but feature is not used. So as it is not used, it's not tested, there is bugs. So what happens? Our very first attempt to use condy unfortunately happened past the release of 11. It happened when they started working on 13. So at the time of working on 13, we discovered that condy of array type causes JVM crash easily. Fix it. Fix was super easy. In one switch in JDK, there was added one more condition. In case of arrays, we should do that. Backported back to two versions, to 11 and to 12. Unfortunately, again, as there is a range of JDKs where this crash presented, we need a workaround. So, well, okay, we couldn't use Boolean type for condy. Let's use object, and let's always cast the object to the Boolean array. That works. Story continues. Unfortunately, we decided to slightly change the way we do a little bit of initialization. And when we do initialization, we need to throw an exception signaling that configuration is wrong. And it happens that initialization is static initializers, and so sometimes happens that static initializer throws exception. In presence of condy, this crashes JVM. Unfortunately, again, found in 14, backported to 11, 13, not 12. This is, by the way, a nice sign of what you should be using and what not. Either latest LTSs or the latest. Nothing in between doesn't exist. It's just intermediate versions, nothing backported to them. Well, workaround was simple for us. Don't throw exceptions. That works. OpenGNI. Same thing. Nobody uses condy, it's not tested. Each use of condy just results in the fact that JVM crashes due to missing garbage collector barriers. Already fixed. I don't unfortunately know. They have a little bit crazy scheme of numbering, so I don't know in which versions. But again, it was fixed later and then backported for 11 LTS. So that's it. That's the end. I hope you enjoyed a little bit of quirks and internals of JVM and what we have to do to compute code coverage for you. I hope you had fun. Now that you know internals, please get involved. Please participate. Answer questions on Stack Overflow. There is JaCoCo tag. Now you know really deep how that works, so you could answer tricky questions. There is users mailing list. Again, you could help us to answer easy questions like, why using reflection I am getting +1 field, +1 method? Well, ignore syntactic members. That's it.